Welcome to the Public Exam Review for Unit 9, Chapter 11. This chapter deals with permutations, combinations, and the binomial theorem. In this presentation, we will focus on the fundamental counting principle. Here we will focus on using graphic organizers, such as tree diagrams, lists, to count the total number of possible choices. We will also solve counting problems involving the fundamental counting principle. We will define a factorial, and we will also define a permutation and identify situations when to use permutations. In this situation, we have a person went to a used car dealership to purchase a new vehicle. There were two types of vehicles to choose from, a car and a truck. They could also choose among the colors black, red, and white. There were also two types of transmissions, automatic and standard. How many different vehicles are possible? We will take this situation and represent it using such graphic organizers as a tree diagram. We will also use an organized list as well as an outcome table to represent the information in this situation. So here we are purchasing a vehicle. The two types we have to choose from are a car and a truck. The colors B represents black, R for red, W for white. So we can have a black car, a red car, or a white car, or a black, red, or white truck. As well, we have two types of transmissions, A for automatic, S for standard. So in the first situation, we have a car that is black with an automatic transmission. Secondly, we have a car that is black with a standard transmission. When we use this tree diagram to illustrate all the possible choices that we have to make, you can see there that we will have a total of 12 choices. As well, we can use an outcome table to represent the same information. The vehicle type will be recorded as C for car, T for truck. The colors, black, red, and white, represented by B, R, and W in each case, as well as A and S to represent the automatic and standard transmissions. Again, when you count the number of choices that are possible, it results in 12 choices of the different types of vehicles possible. As well, we can use an organized list. We begin with C to represent the car, B to represent the color black, and two choices, the automatic or standard transmission. So CBA represents a car that is black with an automatic transmission. Lastly, we could have a truck that is white with a standard transmission. So you can organize the information in the list. The fundamental counting principle is a means of finding the number of ways of performing two or more operations together. If one task can be performed in A ways, in this example, we will use the choices that the car and the truck. So we have two choices in a car and a truck. The second task can be performed in B ways. So then you could select which color, black, red, and white. And the third task in C ways is an automatic and a standard transmission. So all the tasks can be performed together in A multiplied by B ways. So in this case here, the choices in either a car, we have a choice between a car and a truck, so there's two choices. Multiplied by the colors, we have three choices in color, black, red, and white. And we have two choices in the type of transmission, standard and automatic. So when you multiply these together, you have 2 times 3 times 2, which is equal to 12 different possible vehicles to choose from. That represents, the fundamental counting principle is a shortcut way of calculating the number of different possible arrangements. So we also have what is called a factorial. And a factorial is an abbreviation for the product of successive positive natural numbers. It is defined as n factorial, which is equal to n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, and the pattern continues until you multiply 3 times 2 times 1. where n belongs to the set of natural numbers. Here are some examples. 4 factorial is really equal to 4 times 3 times 2 times 1, which we can calculate to equal 24. 3 factorial equals 3 times 2 times 1, which equals 6. 1 factorial is equal to 1, and it is important to remember that 0 factorial is equal to 1. A permutation, on the other hand, is an ordered arrangement of all or part of a set. It's important to remember here the key words are ordered arrangement. The order in which a number of objects is selected from a larger group of objects is important. So I'm asking you here to identify the situations in which order of selection is important. So in the first example, determining the number of outfits you can make when you have 4 pairs of pants, 2 shirts, and 3 pairs of shoes to choose from. Notice in this case that order does not matter because you could select the shirts, then the shoes, and then the pants. You would still get an outfit, whereas if you selected pants, the shoes, and then the shirt, you still get another outfit. So in this case here, order does not matter. Order does not matter. This would be an example of a combination, which we will review in a later section. In the next example, selecting from 4 possible applicants for a managerial and a clerk position at a department store. In this case, order does matter because the applicant cannot be both a manager and a clerk at the same time. So in this case here, order does matter, so this would be an example of a permutation. In the third example, we have the number of 3-digit codes that you can make using the digits 1, 2, 3, 4, and 5 to open the lock on your locker. In this case here, the key word would be code. Because if it's a code, then order does matter, and it too will represent a permutation. Making a fruit salad that consists of 2 types of apples, red and green grapes, raspberries, and strawberries. In this case, you're making a fruit salad, and order does not matter because it doesn't matter if you put in the red and the green grapes first, and then the apples, and then the strawberries and raspberries. So order does not matter. The fruit salad would represent a combination. 50 runners participate in a race. Medals are only awarded to the runners who place first, second, and third. Again, the key words here is that they place first, second, and third. So order does matter, and this would represent a permutation, from which we have 50 runners, and we have to select 3 in a proper order for first, second, and third place. Selecting positions for president, vice president, and secretary from a committee with 30 members. Again, order is important because we cannot have, out of the 30 members, 1 member cannot represent 2 or more positions. So in this case, we will select the president first, then the vice president, and then the secretary. So order does matter, and this would represent a permutation. Issuing a license plate number for a new vehicle that contains 3 letters and then 3 digits. So order does matter, and this too would represent a permutation. So it is important to be able to distinguish when to use a permutation and when to use a combination. And we will provide you with some more situations later throughout this unit in which you can identify and distinguish between permutations and combinations. Let's look at some examples. In example 1, at the ice cream parlor, you could choose between 4 flavors of ice cream, 2 types of sauce, and 3 different toppings when ordering a sundae. How many possible sundaes could be ordered? Let's answer this question by using the fundamental counting principle first. So it is important to also recognize here that order doesn't matter. So it doesn't matter if you put in the the toppings or the sauce or the ice cream, you're still going to get the sundae. So order doesn't matter. So this would be an example of a combination. In the meantime, you have 4 flavors of ice cream to choose from. So that would be 4 multiplied by, we have 2 types of sauce to choose from, and 3 different toppings. So it would be 4 times 2 times 3 would give us the possible number of sundaes that could be ordered. So 4 times 2 is 8, times 3 is 24 possible sundaes. We could also use a tree diagram to represent this information. So some questions may request that you use a tree diagram. So let's do it this way. Let I1 represent the first flavor of ice cream, I2 to be the second flavor of ice cream, I3 and I4. So that represents the 4 flavors of ice cream from which we can choose. Then you have 2 types of sauce. So we can have S1 and S2. S1, S2, S1 and S2, and the same thing for the last one. And then we have 3 different toppings for each one. So you can see how we can represent this information using a tree diagram. So we have topping 1, topping 2, and topping 3. And that pattern continues until we get to the last one. T1, T2, and T3. I should have spread out the branches to the tree a little more. And altogether then, we have 24 different possible sundaes. So we have 24 possibilities. Let's look at the next example. Consider the word cat. In how many different ways can the letters be arranged? So notice that we have 3 letters. So we could talk about the first letter, the second letter, and the third letter. So for the first letter, we have 3 choices that we can make. Once we use one of those letters, we only have 2 choices for the second letter. And now we only have 1 choice left for the third letter. So in this case here, if you have the word cat, there are only 3 times 2 times 1 possible ways in which the letters can be arranged. So that would represent 6 different ways. I also mentioned to you earlier about factorials. Notice that 3 times 2 times 1 can be written as 3 factorial, which is still equal to 6. I would also like to represent this information using an ordered list. Just trying to review the graphic organizers that you can use. So if I start off with the letter C, for example, then the other letters would have to be A and T. Or I could use C, T, and A. If I begin with the letter A, then I could use C and T, or then I could use A, T, and C. If I began with the letter T, then I could use A and C, or C and A. So again, this is an ordered list to represent the 6 possible ways, different ways, in which the letters of CAT can be arranged. A briefcase lock opens with the correct 4-digit code. If the digits 0 to 9 are allowed, and a digit cannot be repeated, how many 4 different digit codes are possible? I would just like to highlight something here. You need to be aware of the restrictions, whether restrictions exist in these permutations or not. So it's telling us here that a digit cannot be repeated. And the other thing you need to look at is when we talk about the digits from 0 to 9, how many digits are present in that situation? There are a total of 10 digits from 0 to 9. If you include the numbers 1 to 9, you have 9 digits, and 0 gives you your 10th digit. So in this case here, we are also told that there exists a 4-digit code. So if I look for the first, the second, the third, and the fourth digits. So in the case of the first digit, you have 10 choices that you can make. Because a digit cannot be repeated, then you only have 9 possible choices for the second digit. The third digit, there would only be 8 possible choices. And for the fourth digit, you would have 7 possible choices to make. So this is an example where the fundamental counting principle is easier to use as opposed to a tree diagram, an outcome table, or a organized list. So when you multiply 10 times 9 times 8 times 7, you will end up with 5,040 possible codes. And each one of those codes will be different. In example 4, how many ways can you arrange 5 different model cars in a row on a shelf? So in this case, we're going to arrange 5 different model cars in a row on the shelf. So in the first case, we have 5 choices for which to make. Then you have 4, 3, 2, and 1. So again, we are using the fundamental counting principle as a shortcut way of determining the different ways possible. 5 times 4 times 3 times 1 is equal to 5 factorial, and you can calculate 5 factorial to equal 120 different ways. In example 5, in Newfoundland and Labrador, a license plate consists of a letter, 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 digit, digit, digit arrangement, such as Ch.11.1. How many license plates are possible? So when you consider the number of letters that we have to choose from, the letters of the alphabet go from A to Z. And notice there that there are 26 different letters from A to Z. When we talk about digits, we go from the digits from 0 to 9. And in that case there, we have 10 different digits from which we can choose. In the first example, or in part A of this example, it says how many license plates are possible. Note that it's not making any restrictions. It doesn't tell us if we can use the same letters twice or 3 times. It doesn't tell us that we can't use the same digits over and over again. So if there are no restrictions, then we can use the fundamental counting principle to come up with our example. There's the 3 letters, and then we have 3 digits. So in the first case, we have 26 different letters from which we can choose. But it doesn't say that we can't use the letters again. So in the second case, we would still have 26 letters from which to choose, and 26 letters from which to choose for the third letter. In the case of the digits, we have 10 digits from which we can choose for each digit that we have to choose from. So 26 times 26 times 26 multiplied by 10 times 10 times 10 will result in 17,576,000 different possible license plate numbers. In part B, it says how many license plates are possible if no letter or digit can be repeated. So notice now that we have a condition that must be met. No letter or digit can be repeated. You have to read the questions carefully. So in this case here, if we go and we select the 3 letters again, and we have 3 digits to make up the license plate number, letter, 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 digit, digit, digit. So for the first letter, we have 26 choices that we can make. When one of those choices or one of those letters is used, we only have 25 letters to choose from for the second letter. And now for the third letter, we only have 24 choices that we can make. In the case of the digits, we can begin with 10 digits from which we could select one for the first digit. Then there will be 90 digits to select from for the second one, and 8 digits to choose from for the third. So when you multiply that out, you have 26 times 25 times 24 times 10 times 9 times 8, and that will result in 11,232,000 possibilities. So you can see in these examples that it is much easier to use the fundamental counting principle as opposed to a graphic organizer. In Part C, how many license plates are possible if the vowels A, E, I, O, and U are not allowed? So now we have another condition here that must be met. The vowels are not allowed. So when you consider the total number of letters that we have are 26 letters, but then we have to subtract the 5 vowels that we have. So that leaves us with 21 letters from which we can choose. So again, we can use the fundamental counting principle. There's our letter, 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 digit, digit, digit arrangement. So in the first case, we have 21 letters from which we can choose. Then it doesn't say here now if the digits or letters can be repeated or not, so we can assume that they can be repeated. So for the second letter, we still have 21 letters from which we could choose, and 21 letters from which we could choose the third letter. Then digits could be 10, 10, and 10. And in this case here, we are assuming that the digits can be repeated because it doesn't specify otherwise. So 21 multiplied by 21 times 21 times 10 times 10 times 10 results in 9,261,000 different possibilities. As a summary then of the key ideas that we've reviewed in this presentation, the fundamental counting principle can be used to determine the number of different arrangements. If one task can be performed in A ways, a second task in B ways, and a third task in C ways, then all 3 tasks can be arranged in A multiplied by B multiplied by C ways. We mentioned factorial notation in this presentation, but we will do a separate video production on factorial notation throughout this particular unit. But we just introduced it today as an abbreviation for products of successive positive integers. And a permutation we will also discuss further as an arrangement of objects in a definite order. Thank you for your time and your attention. Good luck as you continue with your review.